It is May 4th, 2011. This is the webinar on vectors. Thank you all for coming to see our webinars. I have to say thank you in general for the continuing interest in these webinars. It's something we're trying to improve every time we do them. So again, if there's comments, suggestions, or anything else, please let us know. You can email us at support@unitronics.com. On future webinars, we will be scheduling one on troubleshooting and debugging. If you have any requests on something you'd like to see or recommendations that we can go over, we'd like to do a little session on a couple tips that either you have found helpful, or if you have a problem you'd like to see, please again send us an email at support@unitronics.com and maybe put webinar in the subject and just let us know what else you'd like to see there. Also, check out our forum where we have a blog that has continually, we've been updating this page with all the previous webinars. So you can go to www.unitronics.com/webinars as a quick link to here. Okay, now that stuff's out of the way. We're going to be working with VisiLogic, of course, and a V570, and we're going to run an example we have here for vectors. Now, to start off, what is a vector? We define a vector as a start address with some length. So if I say a vector at MI10 with length 5, I'm specifically talking about memory integer 10, 11, 12, 13, and 14. Now we have a number of tools that help us work with vectors, but let's talk again about what is a vector. A vector is a collection of information. Instead of having 5 integers randomly strewn about the controller, we've organized our information into 5 vectors, 5 pieces of information in a row. Maybe they're sequential, maybe they are random, maybe it's pressure or temperature that we've been logging, maybe it's an IP address, for example. Our indirect IP function uses a vector of 4 memory integers to store each octet. There's a number of functions that work with vectors. So we're going to look at some simple tools that use vectors here, and hopefully we'll be able to put together some other interesting ideas from this. So let's take a look at our first function. Again, if we click in VisiLogic on vector, we can see all our tools here. I should mention that we're going to be working in VisiLogic without the HMI. We're going to use the Memory tab and the Watches tab and the Online Test Mode to see what the controller is doing. So aside from vectors specifically, one interesting thing we can get out of this webinar is working in VisiLogic online with the controller. Okay. So let's look at our first function. The vector fill, again we can find it here under fill, will store a value into a set length or indirect length of registers. I'm going to go online here. Okay, and we can see below in my memory area, I have a little workspace set out. This first entry is MI0 with a length of 10. If you've never used this before, it's very easy. Let me just come out of the online mode. We can right-click and select Add Row, and we can link to some integer. Again, since it's a vector, we'll say the start of the vector. We'll say, in this case, 15, and hit OK. And we can define a length, 5. So we've defined a workspace that's going to show us memory integer 15, 16, 17, 18, and 19. We also have the option of looking at 8, 16, or 32-bit. If we're working with double words, we can use 32, memory integer 16. We can also display it as an ASCII, binary, hex, or decimal. So this is all very useful, but we're going to work with these predefined ones we have here today. So let me go back online. Again, vector fill is going to store some value into a length of memory integers. If we take a look at this function, we've defined our constant of 0. So we're going to store the value 0. The start address for this vector is MI0, and the length is 10. So we've defined when we run this function to store 0 in all of the registers. This is very useful for initializing or clearing out a section or a chunk of information. If we want to use a workspace in a vector, and every time we start a new process or function, if we want to clear it out or initialize it, we can use a vector fill. One thing I should mention here, we can do it if we click, we can see our available operand types. If we're using memory bits or binaries, it's a little different than if we're using, our other operand types. So we can use the vector fill for all of our operand types. We just have to predefine which one we're using. So specifically I'm showing that this one we've selected bits and we can use memory bits. And this one we're using our other registers and we can work with these. Okay. So I've set up a little space where I have at MI1000 some information. I have a vector at MI1000 to 1009 of memory integers in a row, and I can show you these. Let me go to our operands, and we'll just do a quick go to 1000. So I have sample data from MI1000 to 109, numbered sequentially, 1 through 10, and I have sample data from MI1010 to 1019, which is random. You see it starts at 5, 2, 8, 6, 1, 9, 3, 7, 4, 10. Okay. We're going to use a vector copy tool. What the vector copy tool it does is it allows us to copy a length of information. So if I say in this case our start of vector is MI1000, our destination is MI0 with length of 10, we're going to copy all 10 of those memory integers. I'm sorry, slow down. Okay. We're going to copy with this vector copy from the start address, which in this case again is MI1000, to the destination, in this case MI0, with some length. So this is the vector length, and we've defined it as 10. Yep. If I go back to my memory setup, just make this a little bigger, and we run this function block. When I hit set, we've copied from MI1000 with length of 10 to MI0. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we want to see our vector fill work, we can erase this. Okay, we've written zeros to all these. Let's put that vector back here. Okay. So, the next function block we have, the same vector copy tool, but we've defined a different space. We're now going to copy MI1010, which was the data in random order, to MI0 with, again, a length of 10. So if I click on MB2 and we set this, we see that we've moved the random data. Okay, so all we've done so far is we've defined what a vector is, and we've talked about two tools, the vector fill, which will store some value in some length, and we've used the vector copy. Now, if you're used to using a store direct, you can imagine that we can use 10 store directs, or we can use this vector copy. Again, because it's a vector, we've defined that it's all in the same row. So we can use our criteria of the start address and a length to define the location of all this information. Okay. Now that we have our data in some location, let's look at some tools we can work with. We have a vector sort function. The information that we give this function, we can double click here. Again, vector sort. The information we define here is our start address, MI0, which is our workspace, and the length is 10. And we can decide if we want to sort up or sort down. And the resultant location is going to be MI10. Again, this is not simply MI10, it's MI10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So again, the length defined here is also what we're going to copy to the destination. So here's our MI0. Here's our MI10. Notice I've initialized it and it's set to zeros right now. If we set MB3, we've copied and sorted the information from MI0 to MI10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this was the up option. We can also sort down. Notice we now have the data in descending order. This is interesting and useful if we think about temperature data and we want to sort our information from highest to lowest, either temperature or pressure or even part count. Any information you have that you've been logging or collecting, we can use to sort. Okay. If you look at our next function, we have a vector compare. So we've set this up to compare MI0 to MI10 with a length of 10. Our outputs here are MB5 and MI20. You can see we put MB5 down in this workspace. So what we're comparing is this vector to this vector. If they're the same, we should expect that MB5 will be high and our MI20 will hold the value of -1. If they're different, our MI20 will hold the location of the first value that is not the same. So you notice it's 0 because we have 5 and 10. If we had 5 and 5 and 2 and 2 and then we'll say 2 and 9, we would hold the value of the first position where the information is not the same. So it gives us another little bit of information. If they're all the same, the value is -1. So we can use either our MB5 as a compare and see if the vectors are the same, or we can use a compare to the memory integer. If it's greater than -1 or 0 or above, then we know the vector is different. Okay, so let's take a look at this. I'm going to copy some information again. Let's copy from the vector copy information in order. And let's use our sort. Oops, go that a little further. Okay, so we have the same string now. Notice MB5 is high, MI20 is -1. So again, we can say if MB5 is high, or if MI20 is less than 0, our vectors match. We can hit the sort again, and this time we're sorting descending. MB5 is low, and MI20 is 0, because the first positions do not match. Okay. Along with these functions, we have a min and a max. So if we're looking at, again, the workspace MI0 with a length of 10, MI21 is going to store the maximum value. We should expect this to be 10. I set MB6. Okay, and the value is 10. And if we use the min, we can set this. The value is 1. So if we've been collecting temperature data and we want to sort, we can use the sort functions. If we want to get the min and max values, we can do that with these functions. Okay, let's take a look now at a simple data table example. We've set up our system bit 13, which is the rising edge of system bit 3, or 1 second pulse. So every 1 second, we're going to add 373 to MI23 and save it in MI23. Now this is a simple data generator. It's just giving us some information to use. Information out into a vector. Okay, so this is where these tools we just looked at can start applying. If we want to imagine that this information is from a temperature sensor or is pressure or anything else that you've been logging and you want to work with in the controller. So I'm going to go ahead and I'm going to set MB10 here. What MB10 did is it cleared the row index, and every second it's writing to the data table. Now we have a webinar on data tables. I don't want to go into this too much, but I'll just show quickly. We're writing to table 1. We're taking our data from the generator and we're storing it into our column at the row index MI24. We've used a conditional statement here that says when we get to 10, reset MB10 and stop writing to the data table. So if we want to take a look at the data table quick, we can go online and see the information stored in it. These values were just generated in the last 10 seconds. We'll leave here. And we can use our read columns tool. We're going to pull the information from table 1. The column is temp, and we only have 1. And we're going to read from row number 0 for 10 rows. We're going to store it into memory integer 0. We're going to give it an offset of 0. So again, with these indirect and vector options, the offset would allow us to place it offset from what we've defined as the start vector address. So if we said 10 as the offset, we would store this to memory integers 10, 11, 12, 13 to 19. Okay. But we're going to save it back into, or I should say write it back into our workspace MI0. So let's hit OK. We'll go back online. And we can watch MI0 here. And we'll read the information. Good. And so now instead of the information we had before from MI1000 and MI1010, we have the information we've just logged in our data table. Now maybe it took an entire day to log this information to the table. It really doesn't matter how it got there, but what we have the ability to do now is pull an entire column or a part of a column down into a vector of memory integers, and we can work on it with our tools. Again, these are exactly the same. The vector sort, maybe we can sort these. Let me see from lowest to highest. Again, we can sort from highest to lowest. We can compare, but it's not going to be so interesting. More interesting now, we can get the min and the max from this data that we've logged. Now this is important because the data table is a great tool and it's a great utility for logging and saving and gathering information, but we can't work in the data table with values. We need to pull them back out to the PLC. And pulling them back out as a vector is very important to understand. Again, we have all these vector tools to use to work with this information. If we want to make something that is going to, say, collect and average the information, we can do that. We just need to understand how we're moving the information about. Okay. So this is, again, a simple data table example. The first portion of it was just to generate some information. And then we have this one simple command to read the information back out from a column to a vector. Okay. And we can see that right here. All right. So the next example, just like we did with the data table, we're going to write using an indirect store function. So we can talk about this quickly. If we click on store and store indirect, we'll see that we have a list of store indirect options. Now we have to select the one for the register type we're interested in. In this example, we're going to use the store indirect MI. But if I wanted to store to a memory long, I'd select ML. System long, I'd select SL. So what does storing indirect mean? Storing indirect is a way that we can take a piece of information and dynamically generate a location to store it in. Again, we're going to use the idea of vector and length, or vector and offset. In our example we saw previously, we were generating information in MI23. So what I want to do now is store that information from MI23 into MI0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We saw one example where we pulled information out from the data table to do that. And now we're going to use a store indirect to build a vector as we go along. Now I've predefined this with a length of 10. But maybe you have a project and the interest is 60 pieces of information. We just have to define the length of the vector to be 60 that we're going to work with, and we can modify this to work. But specifically what we're going to do here is when I set MB12, I'm going to reset my pointer, and I'm going to write zeros to MI0 with length 10. So I'm going to clear out this vector. I'm going to prepare our data, our new data, to be written to it. Okay. So when MB12 is set again, SB13 contact every 1 second. We're going to store indirectly. Now, the two parameters we have here are data. In this case, it's MI23. We're going to take the value from MI23, and we're going to store it in some memory integer, which is defined by MI25. So the value that MI25 holds is going to be the memory integer we're going to write to. So if we see that when we start off, we're resetting MI25, the offset or indirect pointer here. So we're going to do our first data log, or I should say indirect write, or indirect store, to MI0. We're then going to increment 25, so we'll see a 1. And when we come around again, we're going to store to MI1. We increment again, it's now 2. We're going to store to MI2, and so on. We've built a conditional below that says when MI25 is greater or equal to 10, reset MI12, so it'll stop this write. Okay. So we're building a vector here using an indirect store tool. I'm going to set MB12, and you should watch the space here, our workspace at MI0. We'll zero out, and then we'll start writing data to it. Okay, so our first, second, third, fourth, fifth, sixth, 7, 8, 9, 10, and we've reset MB12. Okay. So again, this is a simple example of indirectly writing to a vector. We're building a vector. We can easily change this from a length of 10 with this conditional statement to 60 or 100. We don't have to do this based on SB13. We can have any time function we like here. If we want to store information every day or every 3 hours, we can build a timer function for that. Okay. And again, we have our information in our vector. So we can go and you can use our tools, our vector, our compares, or our sorts, or our min and max again. We can also use the data table, write column tool, and we can write all this information from our vector back to the data table. We can do it in a whole column. So again, if we're taking temperature data and we're saving it, we can copy it back after we've modified it to the data table. Okay. Our next function we have is a shift register function. So we've used the vector fill already. We're going to use it again just to clear out our workspace. We're going to use our MI23, which was our sample data, and we're going to store MI23 into the first position, and every second we're going to shift it down to the right. So when we run this, we're going to be interested in copying 9 pieces of data and storing 1. So 9 plus 1 is our vector of 10. Maybe we should run it, and then we'll talk about what it's doing. So again, watch the space here. When I set MB13, we're going to zero it out, and we're going to start copying information down from MI0 to MI9. So 4, 5, 6. Notice that 2077 is moving down to the right every time, and when it gets to the end, it's gone. This is a shift register, or simple FIFO, first in, first out. We're, in this case, only interested in the last 10 pieces of data. So what we're doing specifically here is, every second, we're copying the information from MI0 to MI1 with a length of 9. That's going to leave a hole in MI0, and we're going to store the new information into MI0. And then we repeat this every second. So we copy down 9 items, we shift them down, and we store the new information in the space we have we've made available. Okay, this can as well be done with the data table, and you can see that in the data tables webinar we have. Okay, so shift register functionality is very useful, and this is a simple way to create it, just using a vector copy. All you have to do is remember to offset the destination by 1 from the start, and you set your length in the length parameter. Okay. We have another function that is called num to bit, or bit to num. And again, we can find this vector bits to numeric or numeric to bit. What it allows us to do is take a number, an MI or a DW or any of our registers, and convert them into a vector of bits. So if we see our example information here, we have our 1-second pulse incrementing MI29. You see every second it goes up by 1. Below that we have our numeric to bit function. So again, we have a number, memory integer, in this case memory integer 29, which is a 16-bit value. And we're going to write the binary representation of this number across 16 bits. So our input again is MI29. Our output is some memory bit location. Again, this is going to be the start of the vector, MB100. And we've defined the length. Again, since the memory integer is 16 bits, I've selected 16. So every second, this is updating and writing the vector to MB100. And we can see that below here. We've put in our workspace MB100. Notice that the least significant bit here is flipping every second. And we can watch the binary countdown. If I want to change this representation, I can't change the binary. We can see in the function below it, we're going from bit to numeric. So I'm going to take that same data we just converted to a vector of bits, and we're going to convert it back to a number. Similarly, our start address is now MB100. Our destination is now MI30. And our length, again, is 16. Which you can see here is MI29 and MI30. MI29 is the result of the increment function, and MI30 is the result of the numeric to bit, and then the bit back to numeric. Okay, so why is this useful? Sometimes we store information as a memory integer, like a bitmap, for example, of an error code. A bitmap can contain multiple pieces of information in a single number, but we won't be able to determine which bit is high or not without breaking it out into its, without using numeric to bit. So we can make a couple compares here. We can say when the first bit is high or low, we have one error condition. The second bit's high or low, we have a different error condition. And this is useful because these bits can all be independent of each other without us having to create several different compare statements for a memory integer. Okay. And there's a number of functions that work that way. In fact, if we look in the help file, any of the enhanced functions will have their error messages spelled out, and we can reference those with their bitmap. The last function I have to talk about here is the struct command. Again, vector and struct. This will be familiar if you've worked with Unican, and if you watch our Unican webinar we did last week, you'll remember that Unican protocol is very good at sending information between Unitronics controllers, but we can say it's limited to sending strictly memory integers. Now again, as we pointed out, this isn't really a limitation. If you consider Modbus, if we want to get mixed data, a memory bit, a memory float, and a memory integer, there's 3 separate commands. But if we package or struct our information into one register type of a vector, we can send multiple pieces of information in a single command. So this cuts down on time it takes to transfer information, and it cuts down on transmission overhead in general. So let's take a look at the struct command. The struct command is going to do 2 things. It's going to operate in the struct fashion or in the extract. The parameters we have here, from vector to mixed data locations or from mixed data location to vector. What we're going to do in this first struct is take mixed data and create a vector starting at MI500 with the information listed below. So I'm going to gather memory integer 300. If we look on the right side, we have a column for length. This is the amount of memory integers I'm going to take. Again, this can be considered a vector. We're going to use MI300 and sequentially 301. We're going to take MB300 with length 4, so that means MB300, 301, 302, and 303. Memory float 30, 31, and 32, and double word 30 and 31. Okay. So the important part of this function block is we have to remember the structure we define here. We're using this and we're building a vector at MI500, a memory integer vector, and we're going to store it in 500. We can then send the vector starting at MI500. If we look at the bottom, total bytes is 25. So if we round to the nearest or the highest close even number, that's going to be 26. So we'll have 13 memory integers. If we remember, we can store 2 bytes to an MI, but we can't really say we have half of an MI, so we're going to round up. This is going to be 13 memory integers, a vector with length of 13. So MI500 with length of 13. We can send that. We can send all these different types of data with one single send command. Okay, so if we remember the structure here, we hit OK. We look at the extract now. We want to see that we have the same structure defined from, in this case, it's the same source address because we've saved it into the PLC memory. We're now going to read that back. But we're going to save it to different locations. So what's important here is the operand type and the length. If we put these operands out of order and we change the lengths, we won't read this information back in the same way we've created it. So we're going to save our memory integers now to 302 with length 2. Our memory bits to 304 with length 4. Our memory floats to 33 with length 3. And our double words to 32 with length 2. Okay, so let's go online and let's watch if this works. I'm going to use the workspace I have under Watches now. We see that in our online mode, the value of MI300 is 123. MB300 is set. Memory float 30 is 123.456. Double word 30 is 1234532. Make this a little bigger. When I run the struct, we've converted all this information and we've stored it in the vector at MI500. Again, if we want to, I want to look at it here. We've created this vector here of information. If we go back to our watches, we run our extract. We've written all of our information to the new registers. So we should expect to see that these are the same. We took mixed data, wrote it to a vector in MI500 here, and then we took the information from MI500 and wrote it back to mixed locations. So now MI302 is 1, 2, 3, MB304 is set, memory 33 is 1, 2, 3.456, and double width 32 is 1, 2, 3, 4, 5, 3, 2. So the extract should work. It should pull out the information exactly as it was as it's stored, but again, it's important that these operand types and their lengths be defined exactly as they were in the struct command. Okay, so these are some of the vector tools we have. Again, some of the most basic. Notice there's a couple more that can be found in the help, or if you have any questions, you can, of course, send us an email. These are the basics of working with vectors. Again, one of the most powerful tools we have available is a data table for storing and saving information. If we have to work with the information, we do have to pull it back into the PLC. So using the read and write column tool is very helpful. Another very important topic that we've covered here is this indirect write. Again, what we're saying here is we're taking from our A the value that's in MI23. Let me just set this one again. The value that's held in MI23, and we're pointing to the memory integer to write it to. So MI25 is holding the memory integer to write to. If we set it again, we're writing to memory integers based on that value. Okay, so that's about all I have to say for this webinar with these examples. Thank you all for listening. Again,